Hello, everyone. Okay, so we are approaching the deadline for maths. So today we're going to talk about differentiation, and I'll try to go quickly through some problems. Some of them are going to be quite easy. So you can watch my previous webinars on differentiation too. So I think I've sent out a link previously. Does everyone know where to find the webinars? If you go to the COMPOS website, you find webinars, then there's a link to all of them. You just need to find the playlists. Okay, so easy-ish problems today. So if you're looking for particular ones, yeah, I don't know if right. Hopefully, it will be helpful. Okay, so let's jump into it. Implicit differentiation. Like when you look at the table of derivatives, so this is probably familiar to you. You don't have to know all the functions, but it's that. Actually, you can rewrite every single equation to account for implicit differentiation or just the chain rule. So let's look at the first one, for example. Let's say that it's not f, that it's f of g, and we need to find the derivative f of g, but with respect to x, of course. So instead of x to the power n, we have g to the power n, and this would be n g to the power n minus 1 multiplied by by g with respect to x. So let me do an example. Well, you all know how to use the chain rule. My point is that you are actually doing that here as well. You just don't necessarily recognize it, because this is x to the power n. Well, let me do the example first. Let's say it's sine x to the power 7, and the derivative of that is 7 sine x to the power 6 multiplied by sine x prime. So it's multiplied by cos x. Cos x. Okay, so that's how you use this rule, right? So this is just the chain rule, but this is like the formula for the derivative. And if you think about it, that's what you are doing already. You're doing, let's say you have x to the power 7, and you're finding the derivative. It's 7 x to the power 6 multiplied by the derivative of x. But the derivative of x is 1. So, yeah. So it is 7x to the power 6. So you're kind of doing this already. You're kind of using the chain rule with when you're doing just differentiation. You're just not realizing it because it's just always 1. So, yeah. So that means if you are doing x to the power 7 derivative, that's 7x6 x prime. But x prime is 1, of course. But once you realize this, it's a really easy step to go from y to the 7 is going to be 7y to the 6 y prime. Okay, etc. If you're doing sine y prime is going to be cos y prime. Because as a matter of fact, sine x is cos x prime. But x prime is 1, so you don't write it. Okay, so sine whatever, sine omega, is cos omega times omega prime. Of course, if omega is a constant, that means omega prime is 0. That's why this whole thing becomes 0. It's a sign of a constant. Well, sine of a constant is a constant, and the derivative of a constant is 0. This is just another angle. When you look at just differentiation, you might not have realized this. Oh, I can look at it this way. And this is very helpful when you are doing implicit differentiation. So take any implicit function like hyperbolic sec h y. The derivative of that is going to be minus sec hyperbolic sec of x. So hyperbolic sec of y times say hyperbolic tan of y multiplied by y prime. And that's it. So all you need to modify is to add this term at the end, because the term that actually exists is x prime. Does that make sense? On a scale of 0 to 10, do you understand what I'm talking about? Okay. Oh, nice. Lots of 10s. Okay, so let's find the first and second derivative of y. So here, of course, we need to differentiate. And because differentiation is linear, we're allowed to differentiate term by term. That means the derivative of x squared is 2x x prime, okay, plus 2xy, so it's going to be 2x prime y plus 2xy prime. I'm using the product rule here, and I'm leaving the 2 intact. Minus, here I'm using the chain rule again, so it's 2y y prime equals the derivative of a squared. Well, okay, let's do it. Let's do something you've probably never done before and never will. It's 2a multiplied by a prime. Okay, so x prime, so that's 2x plus x prime is 1, so that's 2y. 2xy prime plus 2xy prime minus 2y prime equals, well, that's equal to 0, of course, because a is a constant, and the derivative of a constant is 0. Now we take y prime to one side, so it's going to be 2y minus 2x equals 2x plus 2y. Y prime is 2x plus y, 2y minus x. So it's x, I'm just going to change the order, y plus x divided by y is x. Okay, that's it. Okay, so that's a very straightforward way. This one, x to the power y equals y to the power x. Okay. Now this is not this is not can you take logs of both sides? I think so. Yeah, you can take logs of both sides before you differentiate that. So we took log. Well, just let it be ln for simplicity. So ln xy equals ln yx. So y ln x equals x ln y. Now we differentiate with respect to x, of course. So to differentiate that, this is going to be y prime multiplied by ln x plus y multiplied by ln x prime equals x prime multiplied by ln y. So I'm using the product rule here. So x multiplied by ln y prime. Ln x prime, so that's going to be 1 over x. Yeah. So y prime ln x plus y multiplied by 1 over x equals, that's 1. So it's just ln y plus x multiplied by ln y. So the derivative of ln y, that's 1 over y multiplied by y prime. And then you just bring them to one side. So y prime ln x minus 1 over y equals ln y minus y over x, and y prime. Oh, we needed to find the second derivative as well. I'll get back to that. Okay, y prime is y prime is ln y minus y over x divided by ln x minus 1 over y. Okay. Now we need to find the second derivative here. So we found the first derivative, and now we need to find the second derivative. Well, we can differentiate this, but that won't be pretty. So I'd rather go back to here and differentiate that. So finding the second derivative. So I take the first equation and I get in this third line, where did the x go? That's a good question. Where did the x go? Yep, you are correct. Thank you. And that is x over y. This is x over y. Thank you. Right, so I take the first equation, or not the first, but over this line, and I differentiate it again. So it's going to be 2 multiplied by x prime, technically, plus 2 y prime plus. Now we use the product rule here. So 2 x prime y plus 2x y double prime minus 2 y prime minus 2y y double prime equals 0. And now we make y double prime the subject, y double prime, open bracket, 2y minus 2x equals 2 plus 2y prime plus 2x prime y. Well, x prime is 1, so 2y minus 2y prime squared. So y double prime is this, 2 plus 2y prime plus 2y plus 2y prime squared divided by 2y minus 2x. Of course, this can be simplified as 1 plus y prime plus y prime squared divided by y minus x. And of course, we can substitute that in. We can substitute y prime from here. It's not going to be pretty. Plus y plus x over y minus x plus y plus x over y minus x squared, y minus x. Is it worth simplifying it? I don't really think so. I don't think we'll get anything pretty if we try to simplify this fraction. I mean, we obviously can, but I'm not going to do it. So here you can do it in a very similar way if you want to find the second derivative. So you from here you just differentiate it again. So I'm just going to differentiate it, but I won't get to the final answer. It just won't take way too long. So differentiating that, that's going to be y double prime ln x plus y prime ln x prime. That's a product rule. Plus, you can use the quotient rule here. So y prime x minus y x prime over x squared equals ln y. So 1 over y multiplied by y prime plus, okay, so this one is tricky. So you have to do x over y prime plus x over y double prime. And then you simplify this, and then you make y double prime the subject, and then you sub y prime, which is ln y minus y over x ln x minus x over y to get an expression for y prime in terms of x and y. Does the derivative not exist as y equals x? Well, let's see what happens if x equals y. We have x squared plus 2x squared minus x squared equals a squared. So 3, so 2x squared. X squared equals a squared over 2. So x is a vertical line. X equals plus or minus a over square root 2. So that's a vertical, two vertical lines. So yeah, the derivative doesn't exist because at this point it's a vertical, yeah, vertical line. Okay, that was a question. What happens if x equals y in the first for the first problem? Okay, moving on. Find the derivative of y equals arctan x. So here we use the derivative of the inverse function. So an inverse function, so if you have y equals f of x, then you can express x as the inverse of y. Okay. And it turns out that at if you take a graph of a function and its inverse, well, you know that if this is f of x, this is minus 1 of x. They're symmetrical. Okay. So at any given point, let's say at point x0, there's a corresponding point y0. And because they are symmetrical, so at x0, dy dx, so it's, sorry, that's the derivative, dy dx. So dy dx at x0 is equal to dx dy at y0. Okay, so we're going to use that. We're going to use that principle. And just give me a second. Okay. So in order to find the derivative of arctan, we can do the following. We can write y equals arctan x. That means x is equal to tan y. Now we find the derivative. Dx over dy. We differentiate that. Uh, Sorry, I'm a bit lost here. Just a second. Yeah, that should be fine. Okay, so dx dy, yes. We differentiate that, and we know that tan y is sine y over cos y. That means that if we want to differentiate tan, it's going to be sine y prime cos y using the quotient rule minus sine y cos y prime divided by cos squared y, which is cos squared y minus or plus sine squared y, because you have the derivative of cos is minus sine, so minus sine minus times minus sine is plus sine squared over cos squared y. This is 1 using the main trigonometric identity. This is 1, so it's 1 over cos squared y. Right, so it is 1 over cos squared y. Now, we don't need to use the chain rule here because we're differentiating x with respect to y. So we're differentiating on y, therefore, well, technically it would be dy dy, which is pointless. Okay, so that's good. So we can say that dy on dx is cos squared y. All right, and now we need to express cos in terms of tan. Why do we need to do this? Because we can't find cos of arctan. Right, so if we substitute this, it doesn't work. So we need to express cos squared y, can be written as sine, so cos squared y over sine squared y multiplied by that's a bit pointless. Can we do it as yes, so we can use cos squared y divided by cos squared y plus sine squared y. Yes, because this is 1, so we are allowed to cos squared y equals that, which makes it 1. You divide top and bottom by cos squared y, which is 1 plus tan squared y. Okay, so finally, we can rewrite this. So dy on dx is cos squared y. But cos squared y can be written as 1 over 1 plus tan squared y. But y is tan arctan x. So we substitute that in. So it's 1 over 1 plus tan squared arctan x, and tan arctan x is actually x, because f of f minus 1 of x is always x. Right? We know this. Therefore, it is 1 over 1 plus x squared. Whew, finally. That was embarrassing. I apologize. So yeah, that's arctan. Here it is. We obtained it. The derivative of arctan. So therefore, arctan x, the derivative is 1 over 1 plus x squared. Okay. So these questions, they're quite straightforward. Like, how do you define the derivative of y prime? Well, you find dx dt, and then you find dy dt, with t as a parameter. It's a parametric equation. And then you find, to find dy over dx, all you need to do is dy dt divided by dx dt. Okay. Does that make sense? Do I need to go through any of the questions? Would you like me to go through any of the questions? Type a letter which you would like to go through, if you would. If not, we can move on to other stuff. Okay, so very straightforward. Okay, sketch the contour lines and then sketch the 3D shape. Okay, so z is the square root of x squared plus y squared. So what are the contour lines? The contour lines is basically the curve for different values of z. So x, y. So suppose z is 1. Well, we can first square it. So z squared equals x squared plus y squared. So it's a circle of radius z. Circle of radius z. So this is a function of two variables, and in 3D, that would be a surface. It would be a surface in 3D. So z is equal to square root of x squared plus y squared. Okay, so what's that? That x squared plus y squared equals z squared. That's a circle, yeah, as I said, circle radius z. So if z is 1, it's going to be like this. If z is 2, it's going to be like this. Z is 3. So the 1, 2, 3. So these are the contour lines. In physics, they're also called equipotential lines. Yeah, we use them a lot, equipotential lines. So contour lines, similar to equipotential, potential lines. So along this line, z is constant. Along any line, z is constant. So you can see contour lines. Contour lines. Yeah, like this on a map. a very similar way. Okay, so on a contour map, you can see, so this line corresponds to a height of 40 meters above sea level. And that's how you can figure out what kind of, is it a hilly, basically, is it hilly or not? Okay. So basically, what do you think this shape is? If it has a contour lines like this, what would it look like in 3D? Parabolic. Parabolic. Well, let's see. Um, so you're thinking something like that. So you have this z-axis, then you have the y-axis, and you have the x-axis. So when z is 0, that's a dot. When z is 1, it's a circle of radius 1. 1, 1. When z is 2, it's a circle of radius 2. When it's 3, when z is 3, it's a circle of radius 3. Actually, these points look like they are on a straight line. So 4, gonna go like this. So what is the shape? It's a cone, of course. It is a cone. That is the equation of a cone. The z equals x squared plus y squared. It's a cone. Let's verify that. My favorite not Desmos, sorry. GeoGebra. Actually, I think Desmos does 3D, but okay, whatever. So here's the axes. We have the x towards us, y to the right. Okay, so z equals square root x squared minus plus y squared. Oh, yeah, it is. It does look like a cone. And if we look from the top, so the contour lines is just these. Now, if it was z squared, no, that wouldn't help. Nope. Z. If it was like this, then it would be a paraboloid. How would you plot a sphere? Yeah, that would be a x squared plus y squared plus z squared equals, I don't know, 25. No, not 25, 4. Yay, it is a sphere. Sphere with center. Yeah. So this is an implicit function. Yeah, a sphere is an implicit function of three variables, whereas a paraboloid is an explicit function. Because you can't, for a sphere, you can't write z equals something. It doesn't work. But for yeah. Okay. So, oh, that's not what I wanted. Z equals square root x squared plus y squared. Okay. Another interesting one is, I think it's this one, this, but with a minus. Okay. It's a hyperbolic, or wait, parabolic hyperboloid, I think. Anyway, it's hyperboloid. Not very easy. It's also called a saddle. Can we limit x? X is less than 2. Can we do that? Yes, we can. X is greater than minus 2. And y, can we do that? Y is less than 2. Will that work? No, it doesn't like it. Well, yeah, so it's a saddle, basically. And the interesting thing about the saddle is that it's made up of straight lines. Like, you can draw a straight line along the surface, going through the origin. So I can't, don't know how to show it, but basically you can draw something like this. So like this would be a straight line. No, I don't think it's through the origin, but you can draw a straight line. So it's made up of straight lines, which is quite fascinating. You can look those up. Okay. Finally, we move on to the partial derivatives. Partial derivatives is when you find a derivative with respect to something, assuming everything else is constant. So it's quite interesting. So for example, you want to find du dx, or you can find du dy. That's the partial derivatives of the first order. And you have d squared u dx squared, d squared u dy squared, d squared u dx d delta x delta y, and d squared u delta y delta x. So the last two are actually the same. and that's the second order. Okay, so how do you find the partial derivatives? Well, we just differentiate du, delta u, delta x. So when we differentiate that, we assume that y is a constant. So here we use a product rule. So x multiplied by sine. So it's dx dx multiplied by sine x plus y plus x multiplied by dx sine x plus y. So for the latter, we need to use the chain rule. So this is 1. So that's equal to sine x plus y plus x multiplied by cos x plus y. And then, well, it is a chain rule, but it's going to be 1. So that is the first derivative, d delta u delta x. Now delta u delta y. Now we assume that x is constant. All right, and that becomes quite easy because now it's a constant. We can say that it is x multiplied by cos x plus y. And that's it. Because x is a constant, so we take it out. We just differentiate the sign. So it becomes cos x plus y. Okay. Now if you want to find the second order, derivatives, we take the first order derivative and differentiate it again. So d squared u dx squared. So we differentiate that. So that becomes cos x plus y plus, now if we want to differentiate this with respect to x, so it's going to be 1 multiplied by cos x plus y plus x multiplied by sine x plus y. Now d squared u dy squared, we differentiate that, it's going to be cos x plus y plus x multiplied by sine, or minus sine x plus y. And I think, yes, there's a minus here as well. Okay. And then d squared u dx dy. So we differentiate the y with respect to x. So this is delta x of delta u delta y. So that is, we differentiate with respect to x this expression, x multiplied by cos x plus y, and that is going to be, did I go wrong somewhere? Yes, I have. When I was differentiating du dy, but x has to be constant. So here, this is 0 because it's x prime. It's the derivative of x. So minus. Okay. Now, I differentiate this with respect to x. This is going to be 1 multiplied by cos x plus y plus x multiplied by sine, so minus sine x plus y. All right. Which is, yeah, so that's cos x plus y minus x sine x plus y. I will demonstrate that if you do the other way around, d delta squared u delta x, delta y delta x, that's delta delta y of delta u delta x. So we would differentiate this expression with respect to y now. So d delta delta y of sine x plus y plus x cos x plus y. And we differentiate that. That's going to be cos x plus y. We differentiate that with respect to y. So x is a constant now. So that's going to be minus x sine x plus y. And you can see that this and this is the same thing. So it doesn't matter how you do it. So this way or this way, you will get the same result. Okay. So here, d u d delta u delta x. So we treat y as a constant. So we just differentiate the cos. So that's going to be minus sine x squared multiplied by 2x divided by y. Delta u delta y. Now we treat x as a constant. So we can rewrite this as cos x squared multiplied by y to the power minus 1. So it's going to be cos x squared y to the power yeah, so that's going to be minus cos x squared divided by y squared. Okay. Now if you want to find the second derivative, x squared, so differentiate that with respect to x. So y is still a constant, so we don't touch it. So we differentiate the top. So it's going to be minus cos x squared multiplied by 2x multiplied by 2x minus sine x squared multiplied by 2. Can we simplify this? Not too much. So minus 4x squared cos x squared minus 2 sine x squared divided by y. Now delta squared u delta y squared. So we differentiate this with respect to y. So this can be written as minus cos x squared y to the power minus 2. So that's going to be 2 cos x squared y to the power minus 3, which is 2 cos x squared y cubed. Now, if you want to find the second derivative, the mixed second derivative, so dx dy, so we can choose. Either we differentiate this with respect to y, or we differentiate this with respect to x. I'm going to differentiate the top one with respect to y. So it's going to be d delta delta y of minus sine x squared 2x over y. It's y to the power minus 1. So it's going to be plus, so 2 x sine x squared multiplied by, well, y squared over y squared. That's it. Okay, so I hope that makes sense. I hope that makes sense. So I'm just differentiating. This next one, this is a function of 3 variables. And here you just need to find du d delta u delta x, delta u delta y, and delta u delta z. They're going to be very similar. So I'm just going to write it as x squared plus y squared plus z squared to the power minus a half. So differentiating with respect to x, that's going to be minus 1/2 x squared plus y squared plus z squared to the power minus 3/2, and then multiplied by the derivative of the inside function, so that's 2x. Okay, so can we make it prettier? Well, we can cancel the 2, so it's minus x divided by square root of x squared plus y squared plus z squared cubed. In a similar way, this is minus y over square root of x squared plus y squared plus z squared cubed. And same for z, it's minus z, but just from the point of view of symmetry, plus z squared cubed. Okay. If you that's all I have for you for today. Slightly shorter session today. You can go to our YouTube channel and you will find playlists. And if you go to year 13 webinars from last year, and it's one of the first, I think it's webinar 7. Yeah, webinar 7 and around that. So yeah, please have a look. And basically, I'll leave you here. How's math been? Have you well, first of all, okay, if you have you found this session useful for yourself? Just type 1 or 0. Did you find it useful? You don't have to type 0 if it hasn't been useful. Okay, so you found something useful for yourself. You can watch the other webinars, and yeah, enjoy finishing the assignment, and yeah, submitting it on Sunday by Sunday. All right, see you everyone then.